Hi Year 10 and welcome back. This is our second lesson for logarithms, and in this video we're going to look at log laws. Let's have a look at what we learnt last lesson. We learnt the definition of a logarithm. We learnt how to write logs in index form and then how to take index form and write it in log form. And then we looked at the special results. So as I mentioned, this video is about the log laws, but let's start with the index laws. Remember, there are three of them. The first one says, when we multiply numbers or pronumerals that are the same, we add the indices. Second one, when I divide numbers or pronumerals that are the same, I subtract the indices. And the third one, when I raise a power to a power, I multiply those powers. And there are three logarithm laws as well. Here's the first one. When we add logs that have the same base, we multiply the arguments. The second one, when we subtract logs that have the same base, we divide the arguments. And then finally, this is log base A of B to the power of C. And in this case, the C can come down the front and we get C multiplied by log base A of B. My students like to call this the clog law. Okay, we're going to look at the proofs of the first and the third log laws. It's really important that you understand where these things come from rather than accepting them at face value. You won't have to reproduce one of these proofs in an exam or a test, but see if you can follow each step. We're going to start with the first index law. A to the power of m times a to the power of n is equal to a to the m plus n. And our first step is to let x equal a to the m and y equal a to the n. Now what I'm going to do is change both of these statements into log form, which is going to give me m is equal to log base a of x and n is equal to log base a of y. Let's have a look and see if that makes sense. This is a to the power of m equals x, which is correct. A to the power of n equals y, which is correct. Now we're going to substitute back into the original expression. So instead of a to the m, we're going to put x, and instead of a to the n, we're going to put y. Okay, now turn this into log form. So we're going to get m plus n is equal to log base a of xy. Let's see if that makes sense. A to the power of m plus n is equal to xy. Yes, we're nearly there. Have a look at this. M is equal to log base a of x. N is equal to log base a of y, and there it is. There's our first log law, proved. Now I'm not going to prove the second log law because it's pretty much identical to the first one, and you might like to have a go at proving the second log law and see how far you get. But the proof of the third log law is significantly different, so let's have a go at it. So there it is there, log base a of b to the power of c is equal to c times log base a of b, and we're going to start with the right hand side. That's what RHS stands for in a proof. So the right hand side is equal to c lots of log base a of b, so let's expand that out. It's equal to log base a of b plus log base a of b plus dot 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 plus log base a of b c times. Now from our first log law, we know that when we add logs that have the same base, we multiply the arguments. So that's equal to log base a of b times b times b times dot 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 times b, c times. Okay, and we know that from index notation that b times b times b times dot 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 times b, c times is b to the power of c. And there it is. There's the proof. That's equal to the left-hand side. So let's look at how we use the log laws. Now mostly they're just going to be an exercise in arithmetic or algebra. How do we simplify log x squared plus log x cubed? Okay, the first thing and the most crucial thing is to check that the bases are the same. Are the bases the same here? Yes, they're both base 10. So our first log law says that when we add logs that have the same bases, we multiply the arguments. So this is equal to log of x squared times x cubed. And x squared times x cubed is x to the power of 5. So that's our answer. How about this one? Log base 5 of 50, take away log base 5 of 2. The bases are the same. So when we subtract logs that have the same bases, we divide the arguments. So that's log base 5 of 50 divided 2, which is 25, and we can actually work this one out because it's numerical. 5 to the power of what gives us 25? 5 squared is 25, so our answer here is 2. And how about this one? 2 times log base 3 of x take away log base 3 of 3x squared. Now we've got a problem here because we can't have a number at the front. All our log laws are just set in terms of just log of something, take away log of something, or log of something plus log of something. Nowhere does it say 2 lots of log of something. So we need to get rid of this 2. Now what we're going to do is use the third log law. This 2 can come up the top here as a squared. It's kind of like the reverse of that clog law. All right, now we've got log of something, take log of something, so I can divide these 2 arguments, and that's going to give me x squared divided 3x squared, which is a third. And we can work this one out too, can't we? 3 to the power of what gives me a third? 3 to the power of -1. Our answer is -1. Here's another example. Solve the equation log x plus log x squared is equal to log 27. Okay, first thing, check the bases are the same. They are, because they're all log base 10. So when I add logs that have the same base, I can multiply the arguments. Which is going to give me log of x cubed on the left-hand side. And because I've got log of something equals log of something, these somethings have to be equal. So x cubed is equal to 27. It's just a simple equation now to solve. Do the cube root of both sides. X is equal to 3. Okay, just before we move on, I want to look at some common mistakes that students make. Here's the first one, and I've mentioned it before. 2 log 5 plus log 3. So people ignore that 2 that's sitting out the front. And they just look at the base. They say, are the bases the same? Yes, they're both log base 10. And so they say that this is equal to 2 log, and then they multiply the arguments and get 15. But it's not equal to that. Okay, it's actually equal to log of 5 squared times 3. Or you could do 5 times 5 times 3. But it's equal to log 75. So just be careful when you've got a number at the front. Here's another common mistake. They forget the log law, and they forget that this has to be an addition, and they go, oh, okay, in this situation here, I'm going to add the arguments. So they just get it mixed up, and they end up with log base 2 of 12. But it's not equal to that. In fact, what we would do in this situation here is work this out. 2 squared is 4, so that's equal to 2. 2 cubed is 8, so that's equal to 3. And so this is actually equal to 2 times 3, which is 6. So just be aware of those mistakes. Let's have a look at how we might use the calculator for logs. If we're using a scientific calculator, there are only 2 log buttons on the calculator, and they are here. There's one that says log, which is log base 10, and there's one that says ln, LN, which is log base E. It's called the natural logarithm. So what's E? Well, we're not going to do a lot with E in year 10. We're going to wait till years 11 and 12 to look at it in more detail. It's actually called the natural number. Sometimes it's called Euler's number, after the mathematician who discovered it. And it's an irrational number like pi. Coming back to our scientific calculator, suppose we want to find to 2 decimal places log base 10 of 19. All we do is hit the log button and then 19 and press equals. And to 2 decimal places it's 1.28. If we want to find log base E of 7, we would do ln 7, and that's 1.95. Now you're probably asking the question, well, what about if it's a different base, like log base 3 of 12? On a scientific calculator, there are no more options. There's no more log tables. On a graphics calculator, you can do it. You could do log base 3 of 12, but we do have a sneaky trick up our sleeves to be able to do log base 3 of 12. And it's called the change of base rule. So if we want to work out log base 3 of 12, for instance, then there's the rule that we're going to use, because it takes any logarithm and changes the base of it. So obviously, in order to work that out on the calculator, we really want to change the base to either 10 or E. It doesn't matter which one, as long as they're both the same. So let's have a look at it. Log base 3 of 12. Let's change it to base 10. Log base 10 of 12 divided by log base 10 of 3. Put it in the calculator and we get 2.26, etc. And so that's the simplest way to work out a logarithm of a base other than 10 or e. Let's look at the proof because it's quite interesting. We're going to start with y is equal to log base a of x, and then we're going to turn that into index form. So remember that that is a to the power of y is equal to x. Okay, now I'm going to take logs of both sides, and this is a technique that we're going to explore in more depth in video 4 when we're solving equations. So I've got log base b of a to the power of y is equal to log base b of x, and I can do that providing the bases are the same on both sides. Okay, this looks like that third log law, the clog law, remember? So the y can come down the front, and we're nearly there. I'm going to divide both sides by log base b of a, and there we have it. There's the change of base rule. Okay, so let's have a look how we change the base of, say, log base 7 of 141. Now, suppose we want to change it to base 4. I'm not sure why we'd want to do this, other than just an exercise in arithmetic, because we can't put it in the calculator. But suppose we did want to do it, it would become log base 4 of 141 divided by log base 4 of 7. If we wanted to change it to log base e, it would be log base e of 141 divided by log base e of 7. If we wanted to change it to base 10, we would do log base 10 of 141 divided by log base 10 of 7. But here's the interesting thing. They're all going to be equal to the same thing. So if you could put this in the calculator, we could do that in a graphics calculator. We would get 2.54. That's abbreviated to 2 decimal places. These two, check them out on your calculator. It doesn't matter whether we use base e or base 10 or base 4 or base 39. We're always going to get the same value because this is the value of log base 7 of 141. Okay, that's it for this lesson. In our next lesson, we're going to look at log graphs.